So this is about reparameterization. So it solved the problem of the gradient. So let us get back to our gradient computation. So let me just copy this diagram. Let me call it xi, because let's say that we are looking at one particular sample of input data, and we also need the decoder here. Okay, so what is the data flow? As I said, now given an xi, it passes through the encoder network and gives you a mu of xi and a sigma of xi. Then what do? That we sample an epsilon j from normal 0 1. All this happens outside the neural network. Okay, and then we find a zj. Let me call it epsilon I here. I don't want to confuse you with multiple indices. Zi. So Zi is given by just do reparameterization, mu phi of xi plus sigma phi of xi times epsilon I. This is the reparameterization. Now we will take this Zi and pass it through the decoder. Okay, so I think I made a mistake with the length of this diagram. See, typically what happens is the dimensionality of x is much higher compared to that of the dimensionality of z. So we'll have to represent the encoder this way. Okay, so let me try change this here as well. I hope that you are following what's happening. So here the dimensionality of the input data x is in rd, right, and the latent variable is in dimensions rk, and we have, I mean, in a typical setting, the dimensionality of the latent space is much lesser compared to that of the data space. So this is mu phi of xi. Just for the sake of completeness, it's obvious, but let me say, so this is some xi is in rd, which is the dimensional space. My zi is in rk, which means that the mean that I have will also be in rk, and the covariance matrix will be in a k cross k dimensional space, right? So that is what the idea is. Now in a usual implementation, what is assumed is that this sigma matrix, which is the covariance matrix, is assumed to be a diagonal matrix, which puts it to rk, because a diagonal matrix will only have k elements, right? You can take the rest of them to be 0. Okay, so then we have the decoder network here. So decoder network takes this Zi that we have gotten from the sampling as an input, okay, and this is p theta of x given z, and we will get back the parameters of p theta of x given z. Okay, still not told you how to get the parameters of p theta of x given z. Just bear with me for a while now. So this is how the gradients, see, the forward flow is happening, the data flow is happening. Now what we should do is, we are interested in computing the gradient of the expectation of log p theta x given z with respect to q phi of z given x. So this is the gradient that we wanted. Okay, now with reparameterization, what we have done is that we have written this gradient with respect to the expectation of log of p theta x given. So now what is z here? Z is g times epsilon. Okay, this is the reparameterization that we have done, and this expectation is now with respect to p epsilon, right? So this is now equal to the gradient of, now this expectation now will be written in terms of sample averages. Okay, so this is log of p theta x given g. So this g will be of, okay, g of epsilon I, epsilon j, which can be computed now. Okay, so now with reparameterization, what we did was, whatever this expectation with respect to q phi, which was not compute, which was hard to compute, was represented using an expectation with respect to p epsilon, so which can be computed now. Okay, so now where is this m coming from? See, what's happening is, for a given mu and sigma, for a given input sample xi, one can obtain multiple samples of epsilon. So there is no need that a given sample of xi here in the input corresponds to only one sample or one latent sample. Okay, latent vector. Now for a given, for the same given xi, there can be multiple latent vectors zj's, okay, that are passed as input to the decoder. Now that is what is represented as j here. Now suppose you have, okay, let me write that. So here epsilon 1, epsilon 2 up to epsilon m, they are all being sampled from p epsilon. So what we are saying is, for a given data sample xi, we can sample multiple latent vectors using the reparameterization trick. Also we should try to, just to be sure, so we have the zi is now actually being sampled from q phi of z given x, okay, which is equal to a normal distribution with mean equal to mu phi of xi and sigma phi of variance equal to sigma phi of xi. Now why is this important? We'll just pull it a little down so that this is better. Okay, why is this important? See, we actually wanted samples from q phi of z given x, right? That is what we wanted samples from, which was a normal distribution with mean mu and sigma, the variance epsilon, variance sigma. But we could not, we could not get that, or rather, if we get the samples from that distribution, we cannot compute the gradients. So what did we do was simply designated this sampling, okay, in terms of a sampling over epsilon. That's all, right? That is the reparameterization trick. So we can put this in bracket. So we have, technically we have not changed anything in terms of the gradient computation, but we have just made it look a little, easily computable. Okay, so this, I'll put it inside the bracket, inside some box. Now, this is what we wanted, but we did it using reparameterization. Okay, let me write it. So this was this was wanted, right? And this was accomplished using reparameterization. That's all. Okay, the entire process of reparameterization is to accomplish this particular sampling that we wanted by using another auxiliary random variable which is independent of the network parameters. Okay, that is the idea here. Okay, so now this gradient can be computed and we can, as usual, backpropagate. Now, one missing piece of the puzzle here is that how do we compute this log p theta x given g of epsilon j, right? So let us do that now. So to compute, I will write that as p theta x given z. Okay, maybe sake of completeness, let us do it this way. Okay, so how do we compute this? See, all this might look complicated, but I mean, if you go through it carefully, they're all simple math and a little bit of algebra to ensure that the computation that we are doing becomes feasible. Okay, it's not at all complicated. So how do we compute this? Now, in practice, one can actually we can put a log here as well. To compute log of, this is the term that we need to compute, so we'll see how to compute this. Okay, now there are multiple ways to do it. I'll give you one example of how to do it. The basic idea is the following: parameterize p theta of x given z via some distribution, some known distribution, and use the decoder to output its parameters, right? That is what we have been saying, that the decoder and encoder networks in a VAE are probabilistic in the sense that they give you the parameters of the distribution that they are modeling, right? So how do we do? So an example to do this is, let's say that we assume that p theta of x given z. Okay, this is one example of how this can be done, but there are multiple ways to do it. Assume that this is a Gaussian distribution, this is on x, and let's say that the mean of this distribution, let's call that some x cap of z, because x cap of z, x cap theta z. Okay, and let's say that the variance of this particular distribution is identity. Now what does that mean? That means that the decoder here, the parameters of p theta of x given z are actually some mean, okay, which I have called as x cap of theta, and it is taking a zi as an input, right? This is what I'm saying. Okay, so this decoder network now is giving you the mean of this distribution p theta of x given z, which is assumed to have a Gaussian form, and the output of this decoder neural network is giving you the mean of that Gaussian distribution, right? So that is what we are assuming. So now under this assumption, let's see what happens to with the above. Now log of p theta of x given z, what is this equal to? This has a nice form now. This is equal to log of, what is p theta of x given z? That is a Gaussian distribution, which is in higher dimensions we have like 1 by 2 pi, the dimensionality is dt by 2 e power minus x, because it's a distribution on x. So x minus the mean is x cap theta of z. There's a norm here, and since the variance is identity, this is all it is, right? This is how the Gaussian distribution looks like. Okay, so now I can take the constant out. Okay, can say that this is proportional to simply the negative of the exponential here, and the log gets cancelled, so we have x minus x cap theta of z. That's it. Okay, I can use this as the loss function. So now what happened is, this implies that what do we wanted? We wanted the gradient of expectation of log p theta of x given z, and this was with respect to q phi of z given x, right? This is what we wanted. This is equal to the gradient of first we saw that this was equal to the expectation of log p theta of x given g of epsilon, because z was reparameterized in terms of epsilon, right? And this expectation was with respect to p epsilon, and this is equal to, this expectation was approximated using the sample averages, which is 1 by m, and this log was now given by j is 1 through m, and we have a minus here. This is xi minus x cap theta, which is the output of the decoder, zj, that's it, right? So this is the loss that is to be computed, where zj happens to be, so I mean, one might look at this, right? I mean, this, we are seeking the gradient with respect to phi, but this entire thing does not seem to have dependence on phi at all, right? Phi at all, but it does have dependence on phi through the reparameterization, because the zj or zj term that we have here is mu phi of xi times epsilon j times sigma phi of xi, where epsilon 1 through epsilon j are all samples that are coming from normal 0 1. So this is the reparameterization trick. So the loss function here that we have does depend on phi, okay, through z or through x cap theta, where x cap theta depends on zj, and z or z depends on the encoder parameters phi. Okay, so that is how the dependence is. Okay, so let us look at how the gradients for this particular term operate. So let me just copy this diagram because I need this now. Been writing this as sigma times epsilon. Let us see how the gradient computation happen here. Maybe I need a new page. Let us do it here. Okay, now it is no longer parameters of theta. We know that this is we have here x cap theta of z j, right? So this is zj goes as an input, which is equal to mu phi of xi plus sigma phi xi times epsilon j, where epsilon j are being sampled from normal 0 1. Okay, right. So now how does the gradient computation happen? Let's look at this. So I'll denote the forward pass in green color. This is the forward pass. Okay, How does the forward pass happen? The first thing is much for copying it. So forward pass. So first, given an xi, which is a data point coming from a data set D, okay, pass it through the encoder. Okay, so first thing that happens is xi passes through the encoder here. It's like this. Okay, xi is passed through the encoder. So the second thing that we should do is compute rather, so it's not computation. So once you pass it through the encoder, I'll complete it. Encoder to obtain mu phi of xi and sigma phi of xi. So mu phi of xi and sigma phi of xi are the outputs of the encoder. Pass a particular xi through the encoder to get mu phi and the sigma phi, right? So once you get this, one needs to sample epsilon 1 through epsilon m from normal 0 1. This is the auxiliary random variable. Okay, so this is outside the neural network, right? Outside the neural networks. So this sampling happens outside neural networks, and then once you do this, compute z1 through zj, okay, via reparameterization. Okay, z1 through zj are computed via reparameterization, which is this particular equation, and then what we do is pass all of z1 through zj through the decoder to compute x cap theta zj. We'll get m number of, okay, so this is z1 through zm, right? We get m number of decoder outputs, okay, and then what we need to do is just compute this particular term 1 by negative 1 by m, j is 1 through m, xi minus x cap theta zj. That's it, right? You compute this. So now this computation happens at the output of the decoder. So what happens is that xi comes here and we compute zj. I will have to write it in green because we are writing forward pass in green. Once we get all of these are forward pass, so we get mu phi of xi and we get sigma phi of xi. Okay, once we get this, sample epsilon 1 through epsilon m from normal 0 1, and then what happens is we get zj to be equal to mu phi of xi plus sigma phi of xi times epsilon j. Okay, for j is 1 through m, and all these zj's goes as an input to the decoder, and what we compute here are we compute x cap theta zj, that's the output of the decoder. You take the output of the decoder and compute this particular term, which is xi minus x theta of zj, and you sum it over all m's. This is how you do the forward pass. Okay, now we are interested in computing the gradients, right? We need to do the backward pass. So I will write the backward pass in red. So this is the backward pass. So to compute the backward pass, what we should do is that we simply have to compute the gradient of this particular term with respect to phi. So this is 1 minus m. So we need to compute the gradient of this entire thing with respect to phi and then backprop through the following. See, first one needs to backprop through the decoder, right? And then the reparameterization step, and then through the encoder. So when we are backpropagating through the decoder, this is with fixed parameters theta. So because we are only looking at the gradients with respect to the encoder parameters, okay, this is independent anyway. This is independent of phi, and here the gradient is computed with respect to phi. Okay, so let me not write that because that is what we are computing. So what I am saying here is that once we compute the gradient here, so we compute the gradient of this particular term, okay, this is with respect to phi, and then we pass these gradients first through the decoder, okay, with having phi as constant, by having the decoder parameters theta constant. So here theta is constant because this is with respect to phi, right? And then we pass the gradients. So we get the gradients here. We take the gradients and pass it through this particular operation. Okay, and we can compute the gradients with respect to phi, right? I mean, that is the idea of reparameterization. That once we have reparameterized we can compute the gradients with respect to the reparameterization operation, which is the g function. Okay, so gradient is passing with respect to phi here, and this will pass all the way through the input of the encoder. Here we get the gradient with respect to the encoder parameters. Okay, so that's how one backward pass of the encoder parameters happen. Okay, with respect to the first term, we still have to look at the second term. Okay, this is one backward pass for the first term. So now this completes, if you can look at it. So we obtained the gradients of the first term in the elbow with respect to the encoder parameters, and this is with q phi of z given x, right? So the entire discussion so far is to obtain the gradient of this, and all the reparameterization etc. that we did was to obtain the gradient of the first term in the elbow with respect to the encoder parameters. Now we could get that. Okay. Now how do we get the gradient with respect to the second term? Let us look at the second term now. Now to compute, what we need to compute is the gradient of the encoder parameters with respect to the second term in the elbow. So what is the second term in the elbow? It is the KL divergence between q phi of z given x and p theta of z, where p theta of z, okay, so let me write that down. Now p theta of z, it's called the latent prior. So this is the distribution or the prior that is assumed on the latent variable z. So note that this is independent of z. So this is not a conditional or rather latent posterior. This is the prior on the latent variable that we are assuming. So typically this is assumed to be typically assumed to be a isotopic Gaussian distribution or a normal distribution where the dependence on theta is taken out. So we are not saying that it depends on theta anymore. This is assumed to be normal 0 1. Okay. Now remember that in the instantiation that we are looking at, q phi of z given x is assumed to be a Gaussian distribution with mean equal to mu phi of x I or x in general and variance equal to sigma phi of x. This is what we have assumed. Therefore, the scale divergence term between q phi of z given x and p theta of z, the latent posterior and the latent prior, can be now written as the scale divergence between two Gaussian distributions, one with mean mu phi of x and variance sigma phi of x, and another Gaussian distribution with mean 0 and variance identity. Right, this is with the model assumptions that we have made. Okay, now this can be shown to be equal to, please take this as a short exercise and do this. The scale divergence between two Gaussian distributions can be deterministically found out, and that can be shown to be equal to minus half log determinant of sigma phi of x minus the data dimension, k, which is the dimensionality of the latent space, plus trace of sigma phi of x plus the norm of mu phi of x squared. Okay, so please note that all of these are scalars, just like we saw with FID, right, which is the Wasserstein's distance. All of these are scalars because the determinant is a scalar, the trace of a matrix is a scalar, and this norm is a scalar. Therefore, the entire thing will become a scalar, which can be computed. So this can be estimated, right? This can be estimated. And therefore the gradient of the scale term, which is the second term in the elbow, is now equal to the gradient of this entire thing. Right, so this can be computed analytically. It can just simply compute this analytically. So now what happens is, how does this get into in the training of our encoder decoder is that nothing changes in the forward pass, but I'll copy this. In the reverse path, what happens is, so during the reverse path, the gradient with respect to the scale term will simply get added up. Right, so let me call this as term as the grad of KL. Okay, just to I just need some symbol to use that. So what happens is, this thing, while it is after you pass it through the encoder, this thing will simply get added with the grad of KL. That's all. So you add because the gradients are linear, right? You have two terms with respect to which you need to take the gradient. The gradient of the first term and the gradient of the KL term will just get added. So please note that the gradient of the KL is independent of the decoder parameters theta, and therefore if you you can add it here as well, but when you take the gradient with respect to theta, this will be 0. You can simply add those gradients here when it is when the gradients are propagating backwards through the encoder network. Okay, so that's all. So this completes So what happens is forward pass, take an xi, get your mu phi and sigma phi, and get epsilons, reparameterize, pass all those z, j's through the decoder, compute the log likelihood, data log likelihood, compute the gradient with respect to the encoder parameters, back propagate it through all the way through the decoder, and now you can add the KL gradients here, the gradient with respect to the KL term, and those gradients are back propagated all the way through the input of the encoder network. Okay, so once we do this, what we can do is we can update the encoder parameters just by using one gradient step, and we are simply solving the maximization problem here. Therefore, this is alpha times the gradient of j theta q phi. That's it. So this is like one training step for the encoder. Okay, as I said, this seems a little involved, but please go through the lectures again. It's pretty simple. See, all we had to do was get the gradients of the elbow, which is our loss function with respect to the encoder parameters, and the loss function involved two terms. The first is the log likelihood term, the second is the KL term. The log likelihood term involved an expectation with respect to the distribution that the encoder is giving as output, and therefore we could not compute the gradients. We resorted to the reparameterization trick to get the gradients. That's all, right? So once you get the gradients, you can simply use the standard gradient descent to update the parameters. Okay. So now what we need to do is, once we take one training step through the encoder, we need to train the decoder as well. How do we train the decoder? Let's see how to train the decoder. Fortunately, it's not as complicated as the encoder. So let us write it here. To train the decoder, I will say training the decoder. Training the decoder. How do we train the decoder? We simply need the gradients of the elbow term with respect to the decoder parameters, okay, which is equal to the gradient of the first term with respect to theta. So the second term can be ignored, right, because the gradient, or I can just write this, because the second term, right, which is the KL divergence, the KL between q phi of z given x and pz. Please note that we made our pz independent of theta by making it a constant, okay, is equal to 0, okay, because this entire term is independent of theta. I can just ignore that. So all I need to do is find the gradient of this particular expression, which is the first term in the elbow with respect to the decoder parameters theta. So how do I do that is the question. So it's very similar to what we do in the encoder stage. Okay. So let me just write that down. It's very similar to the encoder computation, the encoder gradient computation. So it's the same thing, but what happens is that you don't have to pass the gradients through the encoder network. The forward pass remains exactly the same, okay, but the reverse path only stops here. Let me write that down. So here the forward path does not change. It's the same as that of encoder. Okay, so we get these and we reparameterize, get these as the reparameterized version, xi plus sigma phi xi times epsilon j, okay, j equal to 1 through m. We compute this, and now we don't hold theta as a constant, right? Theta is now variable because theta is the decoder parameter with respect to which we are computing the gradients. That's all. So in all this we hold phi as a constant. Of course, we don't even pass the gradients through phi because we don't need that. We only need the encoder network for the forward pass by keeping phi as a constant through when we are doing the backward pass. That's it. So this is not with respect to theta now. This is with respect to, sorry, this is not with respect to phi, this is with respect to theta. And once we get this, we get our theta t plus 1 as theta t plus something constant times, that's it. So this completes one step of gradient descent on the decoder network. Okay, yeah, so this is how you train a VAE. Let me reiterate how to train a VAE. So we start with one data sample xi. Okay, we pass it through the encoder. This is for the encoder training. Pass it through the encoder, get the outputs of the encoder, sample epsilons from normal distribution outside the neural network, reparameterize them, and then pass all those z's through the decoder. Take the decoder output, compute the log likelihood, which is the first term of the loss. Compute the gradients with respect to phi, backpropagate it through the decoder by keeping the decoder parameters constant, backpropagate it through the reparameterization step, and add the KL gradient, which is the second term gradient, which is a deterministic gradient. Add that, then take backpropagate both of these terms through the encoder network, and then update the encoder network parameters through gradient descent. That is one training step through the encoder. For the decoder training, you do the same thing during the forward pass. Once you compute the output, compute the gradient with respect to the first term, because second term, the loss, the gradient of the decoder network with respect to the second term is a constant, and then back propagate it through the decoder network and use gradient descent to update the parameters, decoder parameters. So that will be one step of gradient through the decoder. Okay, this is one training step through the decoder. One training step for the decoder. So this training has to be done for all the input samples, data samples xi. I just showed it for one data sample. You need to do it for all the data samples. That completes one epoch of training of encoder and decoder, and one can have multiple epochs of training encoder and decoder. Okay. So this completes the training procedure for a variational autoencoder. So in the next module, we will see how to use a trained VAE for doing sampling, or rather data generation. Use this as a generative model, and also use it for posterior inference, or getting the embeddings or features that are extracted from data, that will be extracted from data. We will see that in the next module. Thank you.